Hello everybody, this is Andy Pills. This is the first day of our astronomy unit. We're going to be talking about space this unit. I'm very excited. It's one of my favorite topics. In this introductory lesson, we took a look at how we can use scale to give us an idea of how big things are compared to one another, as well as how far things are apart from one another. Particularly in this toilet paper example, you looked at how we can create a model to show how far the planets are from the sun. In this video, in the first part, I'll actually be using the program that they use in the American Museum of Natural History in their planetarium to show you around space and try to give you an idea of how big things are and how far apart things are, give you a good idea of why they actually call it space. And in the second part, we'll actually be taking a look at this solar system data table and taking a look at a number of different math equations that we can do to also work with scale and get an idea of how much room there is in space and how much distance there is between objects. So in this first part, I'm going to use this program called Open Space. I am a novice at it, but I think I'm getting the hang of it. So we can spin it around and we can see the Earth in space. A reminder from our insolation unit that the Earth is always going to be half lit by the sun, and that's going to be the half that's facing the sun. And the side of Earth that is not facing the sun is going to be dark, and they'll be experiencing nighttime. So I can use this simulator to move forward, and we can just kind of take a look at what this looks like. And that orange line there is showing the orbit of the International Space Station. You'll see that it orbits the Earth many times. And every time the Earth completes one rotation, 1 day passes for us on Earth. So this simulator will also allow us to kind of zoom out and take a look at some of the other planets that are in the solar system and how big the solar system is. So this blue line that we see here, that's an outline of the orbit of the Earth. So that's the path that it's following as it moves around the sun. We can't really see too much of it right now, but we can see the orbit of the moon going around. So we'll take a look at that in just a second. Let's start to zoom out. And if you look up here where it says distance from camera to focus, the focus is our Earth. So right now we're as if we're about 40,000 kilometers above the surface. And if you watch this number now, we're about to move out. So we're increasing our distance from the Earth. There's the moon going around again, just to give you an idea of where the moon's orbit is in its monthly orbit around the Earth. Again, you'll compare that to where the International Space Station is, where we have astronauts orbiting the Earth. And let's keep zooming out. I'm going to pan the camera up a little bit. Oops. How do I do that? There we go. Sorry. Hope no one's getting motion sickness. Let's keep on zooming out so I can spin it again. Now we're starting to see a better outline of the Earth's orbit, but we are still going out. There's the moon's orbit, kind of encapsulated in this frame here. We're going to continue zooming out. And now we're starting to see the orbits of the terrestrial planets. So I am going to stop zooming out here. We are 1.7 AUs away. That's an astronomical unit. That's about 1.7 times the distance the Earth is from the sun. So from here, we can see the orbits also of Mercury, the first planet, of Venus, of Earth, and the red planet Mars. Oopsie, sorry about that. Let's tilt and spin it so we can see the 4 terrestrial planets. And now I'm going to zoom out again from the Earth. And now we're going to start to see our gas giants, or our Jovians. So after Mars is Jupiter, largest planet in the Earth. Then we see Saturn. We're going to go way out. That's Uranus. And one more planet is going to be Neptune. So there is a selfie of our solar system, just to give you an idea of how far out these planets are. So we can even speed up the time a little bit. And pause this. And let's adjust it by months maybe. Let's make this time go by a little bit quicker. So you're going to see those inner terrestrial planets are moving around the sun fairly quickly. And it's not so much the case for those Jovians that are way further out. So we can zoom in again. And just to give you an idea of how much we zoomed out, we are zooming in and back pretty close to the Earth here. So hopefully I'll get better at this program and we will continue using this throughout this unit. But in this next part, I'm actually going to change gears and go to some data. In this next part of the video, we're going to do some math as related to this solar system data table. So in this video, the teacher explains how to make a toilet paper scale to measure the planet's distance from the sun. We'll be doing something not as fun, but hopefully a little bit as creative. So it's going to ask us to create an example, discuss with your teacher how you will execute a scale model and how you will submit your work. It could be theoretical, meaning no waste. We're not going to be using toilet paper. We all know how last year went. So we'll make an imaginary scale to give us an idea of how far planets are from the sun. We're going to use a little bit of data here in this spreadsheet. So what I did is I just took our mean distance from the sun for each celestial object and the equatorial diameter in kilometers. And I also went out and I collected some data on things from my household. So I got my height in centimeters, and I got the length of my cat from the tip of his nose to the tip of his tail. So we'll kind of work with these numbers a little bit and see how they relate to planets in our solar system. So the first thing that I want to do is, first off, now that you know where I got my data from, I'm going to make this a little bit smaller. And I'm going to pull up the calculator because I want to convert units and I want to make everything in kilometers because that's the unit that this table is giving us. It's actually giving us kilometers here and million kilometers over here. So I want to make sure that I'm accounting for that million too. So first off, my height is 180.3 centimeters. In order to convert that to meters, I'm going to divide it by 100 because there are 100 centimeters in a meter. Think of like cent. There's 100 cents in a dollar. Century is 100 years. So I'm 1.803 meters tall. I want to convert that to kilometers. Since there are 1,000 meters in a kilometer, I'm going to divide that by 1,000. And my height is 0.001803 kilometers. A tiny number, which is why we don't give our height in kilometers. If we're in a country that uses the metric system, we would give our height in centimeters or meters. So my cat, we're going to do the same process, 79.0. I'll divide by 100 to find out his length in meters, and then divide by 1,000 to find his length in kilometers. And I'll copy that into my scale. So next, I want to find out, let's say theoretically, if we were going to be making a model, how many copies of me would I have to stack from head to toe to stretch from, let's just go down the solar system, from Mercury, from the sun to Mercury. Well, Mercury is 57.9 million kilometers from the sun. I'm going to multiply this by a million. So that's Mercury's average distance from the sun. And now I'm going to divide that by Mr. Pulse's length. So divided by, and that is how many copies of myself I would have to stack from the sun to Mercury to create a scale. So 0.7, I'm going to round. So Mercury is, I don't even know what this number is. That's a lot. 1, 2, 3, comma, 1, 2, 3. But there are 32 billion 113,144,758.7 is between Mercury and the Sun. Oops, I put that in the wrong box there. So I'm going to cut that and I'm going to paste it. What are you doing, Bill? Boom. All right, and then I can continue that process again if I wanted to find, let's just skip right over to Earth before I put anyone to sleep there. I'm amusing myself. So Earth is 149.6 million kilometers from the Sun. So I'm going to divide that by my length. Let's do cliff. Let's find out how many cliffs it would be. Or no, we can do pieces for comparison's sake. So I'll divide that number by length of me, and here's our number again. Wow. I'm going to round that 6 up since that 5 is there. 7 pulses. Would there be an apostrophe there? I'm not a grammar teacher, I'm a science teacher. So to compare, if we were using my scale, again, I put it in the wrong column here, we just did Earth. If I was using the scale of Pils, it would take 82,972,823,072.7 Pilses to stretch head to toe to reach from the Sun to the Earth. We could do one more. We can find out how many cliffs it would take from nose to tail to stretch from the Earth's surface to Earth's moon. So it says here in this table that the moon is 0.386 million kilometers from the Earth. Let's plug that into our calculator. 0.386 times 1 million. So there's the moon's mean distance, and I'm going to divide that by a length of a cliff. Find so that divided by a cliff. Find out how many cliffs could stretch between the Earth and the moon. Oops. Say the tables. 0.9 cliffs. There's my cat. Let's just plug this number in. Not too many compared to the other ones. It would just take 488,607,594.9 cliffs. I guess I gotta bend part of his tail. I wouldn't do anything to my cat. I love him. All right, so we can look at one more question just because it did ask us to compare the Earth to other planets. So just to take a look at how we would do that, we see that the equatorial diameter of the Earth is 12,756 kilometers. So we can take the diameter of whatever celestial object we wanted to compare it to, and we can divide it by the diameter of the Earth. So if I were to take Jupiter, and it would be the largest diameter in our solar system, equatorial diameter, I would take its value, I would divide it by the diameter of the Earth, and that would be my comparison. So when looking at the planets from left to right, Jupiter would be just over 11 times wider than the Earth. So much, much bigger. And then if we wanted to figure out like the circumference or the area, we can use equations to figure that out too. So I hope you found this interesting. We'll be talking about space and the astronomical numbers that we use to describe the values and the data as we work through it later on. I'll see you next time.